Hello Chem 212 students, and welcome back to our final lecture on substitution and elimination, chapter 7. For the last part, we'll be talking about how to predict the products of reactions and how to draw the correct product. As you can see, or as we've discussed previously, elimination and substitutions are often competing with one another. And so we're going to use a combination of the substrate, right here, the reagent, the solvent, and in the case of a substitution reaction, oftentimes the leaving group as well, and the quality of the leaving group. And so these are topics we've discussed throughout the chapter independently, but now we're going to apply them to determine which products would be produced. So for example, here in this reaction, hydroxide is both a good nucleophile and a strong base, and its substrate is a primary alkyl halide, and so the result is we can have two possible, we can have elimination, E2, an E2 reaction, with two possible regiochemical outcomes. There are no stereochemical outcomes in this case, other stereochemical outcomes, because neither of these carbons would be chiral. We also have the substitution product here as the minor product. So the question is, how can we determine, by evaluating the substrate, the reagent, the solvent, and the quality of the leaving group, which reaction mechanism will be the primary one and which will be secondary ones? So which products will be the major products and which will be the minor products? And so that's what this last part of the chapter is going to be about. Sometimes, depending on the substrate, there is only one possible product that can occur. In this case, this is a strong base and a strong nucleophile. Because it's tertiary, we could potentially have an SN1 mechanism, but for reasons we'll discuss later, we'll have only, in this case, for the elimination at least, we would only have one possible product because of the way that the molecule is arranged here. If we make a double bond in any of these three positions, it's exactly the same molecule. So there's only one regiochemical outcome in this case for this elimination. So to predict the products, we're going to have to do the following analysis. We want to determine the function of the reagent. So we want to take a look at what is the reagent. Is it a strong? We're going to evaluate it on these factors: strong or weak nucleophile, strong or weak base. And of course, bases are good for eliminations. Nucleophiles are good for substitutions, a good nucleophile. And there's a lot of overlap there, which we'll talk about. We want to analyze the substrate and determine what is the expected mechanism. This is going to depend on whether it's primary, tertiary, or secondary or tertiary alkyl halide. And it will also depend on other requirements such as the solvent or the quality of the leaving group. So when we've covered each of these reactions independently, and for a substitution, what we want is we want a strong nucleophile. And for an elimination, we want a strong base. And the favorable mechanisms will be the SN2 and the E2. These will dominate, as we'll see. If you have a weak nucleophile but the correct, a good substrate for it and the right solvent, you can get SN1 mechanism, which competes heavily with the E1 mechanism. And so the reason why these weak nucleophile, weak base support the SN1 and E1 mechanisms will be, as we'll see, mainly because they're not strong. If they were strong, then they will favor an SN2 or an E2 mechanism, assuming that the substrate it allows for that. So when it comes to, if we want to favor, if we're trying to choose a particular reagent to favor a reaction type, if we want an E2 mechanism, what we want is a strong base that is not a strong nucleophile. Because if the nucleophile and base are in competition, you'll have a competition between SN2 and E2. So when we want to make an E2 reaction happen, what we want is a neutral base, like these that contain nitrogen here. Another possibility is sodium hydride. As notice, these are neutral. They have no negative charge to them. And so that's the way you can quickly pick them out. And so, and dBn and dBu, these are shorthand for these structures here, which both contain basic nitrogens that can function as a base, but they're not negative, so they're not great nucleophiles. We'll see that all the great nucleophiles are negative. For example, some examples of strong bases and strong nucleophiles are those with the oxide ions, so hydroxide, methoxide, ethoxide. Great bases, great nucleophiles, so we're going to end up getting a competition between SN2 and E2 when we have these reagents. If we have a reagent that is a weak base but a strong nucleophile, so these include the conjugate bases of our strong acids, and all of these hydrosulfides here, or sulfides, and hydrosulfide here, a thiol, as these are called, or H2S here as well. So something to notice about most of these is that they're negative, right? So this makes them better as nucleophiles. They're not great bases, not these. These over here with the oxide, these will grab a proton quite easily, but the sulfur stabilizes as a larger atom than oxygen, stabilizes the negative charge better. And so that's why these are good nucleophiles anyway, and they're not good bases. Because the negative charge is quite stabilized, so they're not going to go around looking for protons, but they do have a lone pair of electrons that will go and be attracted to an electrophilic site. And then finally, the neutral sulfides here. These ones, again, it's due to that larger sulfur atom which has the weak grip on electrons, and so it can donate them to make a bond. Finally, weak bases and weak nucleophiles include alcohols and water. Notice they're neutral, and when they do a nucleophilic attack, they're going to end up protonated, so they have an extra step of having to be deprotonated after as well to make a neutral product. And so notice how I didn't necessarily memorize which were strong bases or weak bases, or strong nucleophiles or weak nucleophiles. What I did was I understood the reasoning behind what makes them a strong base or a strong nucleophile, right? So a strong base is going to be one that grabs protons. These ones, we know from chapter 3, they do, and these ones don't as much, because we can evaluate the stability of the negative ion using REO like we did in chapter 3. And we saw these here. These are neutral, and they have a nitrogen atom, which isn't like a sulfur atom, large and able to stabilize negative charge. There is no negative charge. But they have a lone pair that they can give to grab a proton specifically. And they can't do much else. Like a nucleophilic attack is not going to be likely with these because of their structure. And so instead of memorizing this stuff, what you want to do is you want to understand why each of these reagents fit into the category that they do. That way you don't have to memorize, right? You'll just know based on their qualities. So then, once you've determined whether you have a strong base, weak nucleophile, or whatever category you have here between base and nucleophile, you can use this chart to determine the reaction. So when we have a strong base, the elimination E2 mechanism dominates here. So there's really no competition for E2 when the base is strong, but the weak nucleophile is weak here. So strong base, weak nucleophile. That's this first box right here. So hydrides and these amines will be the strong base, weak nucleophile. Now, if you have a base that is a good nucleophile, like our hydroxide or methoxide or ethoxide ions, all these alkoxide ions, these are both strong bases and strong nucleophiles. So if the substrate is a primary alkyl halide, the SN2 reaction will be dominant because that nucleophile will be open to the backside attack on the reagent to do an SN2 reaction. There will be some E2 also, so we would say that the SN2 product will be the major product, the E2 product will be the minor product. If the reagent is secondary, then the SN2 reaction is slowed down because the backside attack of the nucleophile is hindered, sterically hindered. So we get a less of the SN2, so the SN2 ends up as the minor product, the E2 ends up as the major product. And if we have a tertiary alkyl halide, the SN2 reaction becomes so slow that the E2 is dominant here. We're going to get SN2 dominant reactions when the nucleophile is not a strong base. So we're talking about the halides, iodide, bromide, chloride. We're talking about the sulfide ions and the thiols, those involving sulfur atoms. So again, remember the SN2 reaction is not going to be favorable with the tertiary alkyl halide because the backside attack will be hindered. So SN1 reaction will be favored for the tertiary alkyl halide, but for primary and secondary, the SN2 reaction will be preferred. Notice there's a weak base here, so that does not favor elimination. So these will favor substitution. Finally, if you have a weak base, weak nucleophile, that generally makes for a slow reaction in general. But if we have a tertiary alkyl halide, remember that the SN1 and E1 mechanisms both involve a rate-determining step that produces a carbocation intermediate. And that carbocation intermediate will be most stable if it's tertiary. And you will get an even mixture of SN1 and E1 products. The secondary and primary carbocations that would result from the first step of an SN1 or E1 mechanism will be formed too slowly, and so you'll essentially get no reaction here. And so that is how you analyze this. Again, notice that you can understand this graph without memorizing it, this chart. Now, I will provide you with this chart on the exam, but I think it's important that you can understand what goes in each box without having to reference the chart. That's very important because that improves your intuition and your understanding of the general features of organic chemistry. So understanding why each of these boxes populated the way it is, as I just described, is extremely important, and you'll want to be able to populate this box in your mind based on your knowledge, because I will ask you for explanations for why is elimination favored here, why is substitution favored here, right? It's not just about getting the right answer, but understanding why it's right. Finally, after you've analyzed the reagent and the substrate, you can determine which mechanisms are most likely. So you draw the possible regio and stereochemical isomers, and then for SN2, you'll observe a single product which will involve the inversion of the stereochemistry at the alpha carbon, because the SN2 nucleophile attacks the alpha position in the backside where the leaving group is, and then the leaving group leaves. The nucleophile replaces the leaving group with an inversion of configuration. So that's something to keep in mind too. For SN2 reactions, you're going to get the stereochemical inversion, and you do have to write it the correct way. If you have an SN1 reaction, remember you're going to have a mixture of a racemic mixture of the products, slightly favoring the stereochemical inversion, but mostly, pretty 50-50. Okay, so let's go through each of these types. Step 3 for each of these types, evaluating the regiochemical and stereochemical outcomes for each of these possible reactions. If we have an E2 mechanism, remember that E2 mechanism has to proceed through the anti-periplanar geometry. So the E2 product, assuming that both carbons start as chiral carbons, you can end up with only one stereochemical outcome. So this is called stereospecificity, right? You also have to think of the regiochemistry. Depending on the base that is used, if you get a bulky base, you'll have a lot of steric hindrance, so you'll end up with the less substituted Hofmann product. But if you have a small base used, such as methoxide, ethoxide, hydroxide, then the most stable alkene will be the major one, the one that's the most substituted. So the Zaitsev product is favored over the Hofmann product unless you use a sterically hindered base, such as tert-butoxide is the most common one. And the process is stereoselective. Remember that you may have to use, when you're doing an E2, you may have to draw a Newman projection of the substrate to make sure that everything is rotated such that the hydrogen is anti-periplanar to the leaving group. And also remember that if you have a cyclohexane ring, the hydrogen and the leaving group will only be anti-periplanar if they are both in the axial position. If they can't both make it into the axial position, then the reaction will not occur at any appreciable rate. If you have an SN1 reaction, and this kind of applies to E1 too, in this case right here, you draw the carbocation intermediate because it's going to be the same carbocation intermediate whether it's SN1 or E1. And you should consider if a carbocation rearrangement is likely. Remember, a carbocation rearrangement may occur if it can produce a more stable carbocation, like a tertiary one, particularly if that will result in resonance, which will further stabilize the carbocation. Remember, in an SN1 mechanism, you will get a racemic mixture, both the R and the S products, so you do have to draw them both. Okay, so the nucleophile will generally attack at the carbocation at the alpha carbon, where the leaving group left. However, there is a possibility for a carbocation rearrangement, so please make sure to look out for that. Draw the carbocation, see if there's any carbocation rearrangements that make sense. And the nucleophile replaces the leaving group, and you get a racemic mixture here. There's a slight preference for inversion, but you're going to get R and S configurations. You have to draw them both. For an E1 mechanism, as I said, like the SN1 mechanism, there's going to be a carbocation intermediate after the loss of the leaving group, so you're going to have to draw that carbocation intermediate, and then you'll draw all the possible alkene isomers that could result from this elimination. And all possible alkene stereoisomers will form. E1 is not stereospecific like E2, right? Because it's happening in two steps. In the E2, we had to have the anti-periplanar rearrangement so that the hydrogen could be removed at the same time that the leaving group is leaving. And the pi bond can be formed from the p orbitals. E1 is not stereospecific. You're going to get a mixture of the stereoisomers if there are two possibilities. The major product will always be the most stable alkene. So in this case, the Zaitsev product for an E1 is always favored over the Hofmann product. It doesn't matter if the base is bulky or not. The process is stereoselective, but it's not stereospecific, right? So meaning that you will get certain stereoisomers that are more stable. You will draw the one that's more substituted always. And you won't draw the less substituted Hofmann product. That's only for a bulky base with E2 mechanism. So let's say we have this reaction right here, and we want to predict the products. So we go through each of these steps. First, we look at the reagent, and we say, okay, how can we describe the reagent? This is a strong base hydroxide. So we have sodium here, but it's just a spectator. What we're really caring about is the hydroxide. So it's a strong base and strong nucleophile. Okay, so we now evaluated the substrate. Strong base, strong nucleophile. We can already tell right away this is going to be, well, let's see. We can't tell right away. We have to evaluate the substrate first. So if we look at the substrate, this is the alpha carbon right here, connected to the bromine. So it's secondary. It's attached to two other carbons. There is a hydrogen. It's not drawn, but it's there. So this is a secondary substrate. So what this tells us is that because it's strong base, strong nucleophile, it could be either E2 or SN2. And for a secondary substrate, notice that we'll get a mixture of SN2 and E2, but the E2 will dominate because the secondary substrates are somewhat hindered. If it were a primary substrate, the SN2 product would dominate, but here our E2 product is going to dominate. And so now we have to write the result of the E2 and the SN2 reactions here. Okay, so the primary product is going to be the SN2 product. And notice what we did here too. So this is SN2. So the thing we have to remember about the stereochemistry of the SN2 is that there is a inversion, right? R to S, S to R, whatever. There's going to be an inversion. We don't have to say, unless we're naming it, whether it's R or S. but there is going to be a stereochemical inversion. So what you have to do is in the product, when you write the product, you replace the leaving group with the hydroxide. So the hydroxide here, I'm going to draw the hydroxide without the sodium. Yeah, sodium's over here, but it's not involved. So the hydroxide has to come in for a backside attack here. Boom. And then the bromine leaves at the same time. So those are the reaction arrows. And so we replace the bromine with the hydroxide. However, remember, there has to be a stereochemical inversion. So the way we draw the enantiomer of the product is that instead of putting the methyl on the wedge here, now it's on the dash. So that inverts from R to S or S to R. And so now we have the SN2 product. But that's not the only product, right? So this is going to be the major product. But we also have to indicate what the minor products will be. And in this reaction, there will be minor E2 products. Now, the thing with the E2 is that, remember, we have to consider if there's only one hydrogen, we have to be very careful. If there's one hydrogen on the beta carbon, we have to be very careful to make sure that we consider the stereospecificity. And in that case, we may have to draw a Newman projection to make sure. But in this case, we don't have to worry about that because there's 2 hydrogens on the beta carbon here, and there's 3 hydrogens on the beta carbon here. And so we do have 2 possibilities here in terms of the ultimate stereochemistry, right? And so we can see that if we looked at a Newman projection, right? So if we're looking at a Newman projection and we're looking right here down this carbon, okay, so this is going to be my center carbon, and the wedges here are going to be the right side because my eye is facing left to right, and the dashes are going to be the left side because I'm facing left to right, right? And so my front carbon here is going to have the bromine going, the phenol going straight down, which I'll call PH, or no, cyclohexane. So I'll call that CH, let's say, cyclohexane. That's probably not a great way to do it. Maybe I should just draw it, because that CH looks like carbon hydrogen. So I'm just going to quickly draw it then. It doesn't take that much time. So boom, 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 boom. So that's the cyclohexane. And then the front, the wedge, we have a hydrogen A, and on the back, we have hydrogen B here. Okay, then on the back carbon, here, the bromine is going straight up. Okay, and the wedge here is the methyl. So the methyl is going to go on the right side, and then there's a hydrogen that's not drawn that's on the left. Okay, and so in order to do this, remember that the hydrogen A or hydrogen B has to be anti-periplanar to the bromine because we're doing an E2 mechanism. So what I'm going to do is I'm going to rotate this front carbon by 120 degrees to put hydrogen A in the correct position to be anti-periplanar to the bromine. And so now I can draw a new one here where hydrogen A is down here. The cyclohexane group is now here, and hydrogen B is right here, and everything on the back carbon has been left the same. So the bromine is here, the methyl group is here, and the hydrogen is here. And now we see that the hydrogen and the bromine are anti-periplanar in the same plane of the page. Great. And so now what's going to happen is our structure is going to flatten, and we're going to make a double bond here. So now let's draw that. So I'm going to flatten it with a double bond here, and I'm going to call this the top, and I'm going to call this the bottom. You can do either side. You can be looking at it from either direction. But notice that the cyclohexane group and the hydrogen B are going to be on the same side in this case, and then the hydrogen and a methyl are going to be CH3 are going to be on the same side. And so you can see here. Oops, let's see. Did I make a mistake? Oh no, hydrogen A was eliminated. Okay. Yeah. Okay, so this is the elimination of hydrogen A. So hydrogen A was eliminated. So notice that we get this trans configuration that we see here. The phenyl group is opposite to the methyl group, right? So we get this trans configuration. Phenyl group opposite to the methyl group. Now mine doesn't look exactly like that one, but you can see it's the correct stereochemistry here, right? The methyl group, and this would be right here, would be hydrogen B, and this would be the other hydrogen. And so if we rotate for that, so the hydrogen B is antiperiplanar, we'll get this other stereochemical outcome. And finally, if we do an elimination here, there's 3 hydrogens. There's going to be no difference. It's just going to be a double bond there. And so these are all the minor products here, and you would have to account for all of them. Which would be the most major of the minor products? Well, it would be the one that's more substituted. So these two are more stable than the third one thermodynamically. These first two, because their double bond is more substituted. It's attached to 2 carbons, whereas here the double bond's only attached to 1. So these are more stable thermodynamically. Also, of these two, this one is more stable of the 2 because the large groups are trans to one another, allowing for less steric hindrance. So you can see there's going to be some steric hindrance here. There's going to be some crowding right in this area here between there's going to be quite a lot between the cyclohexane and the methyl group. And so these would all be minor products. This would be the most major of the minor products. This would be the next one, and this would be the least. Here, and oops, in this case, let's see. Oh yeah, and we said this was a secondary, rather. Okay, this was secondary. So the SN2 product, oops, please forgive me there. This is a secondary, so this is going to be the minor product. My apologies there. This is going to be the major product, and of the major products, this one here will be the most major. So we have this one here as the most major. The other ones are secondary products. And that's how you evaluate which pathway it goes down. Now, my apologies for the error. I forgot this was secondary for a moment. Remember, secondary slows down the backside attack of the strong nucleophile, strong base here. So that's going to cause the SN2 reaction to be slightly slower than the E2 reaction. So the E2 reaction will be the major product. These are the 3 possible products. And this one right here with the trans cyclohexane and methyl will be the most stable one. Sorry for that mistake there. Okay, but that's how you evaluate it. So you simply apply those steps again and again, and that's how you'll determine the products here. Now, one concern is that a lot of the times we have leaving groups that are not great. They don't want to leave. They're not stable when they leave. And what we want is groups that stabilize the negative charge very well when they leave. And so what we're going to see as we move forward into later chapters is a lot of the times when we have a leaving group that's not a very good leaving group, like let's say hydroxide, right? Or like fluoride, for example. Not great leaving groups. They leave with a charge to them. They're not particularly stable. These ones, when they leave with a negative charge, they have massive resonance stability. So here we have resonance here with the sulfate. The sulfate itself has resonance. Here we have a sulfate attached to a aromatic ring, and so we get further resonance throughout the ring with this tosylate. So tosylates, we're going to see these again and again. And here there's resonance with the sulfate, and there's also induction due to the fluorines. And so in terms of leaving groups, the tosylate will be the best one, the triflate will be next, and then the mesylate will be last. These are excellent leaving groups. So later on, when we get to reactions like the alkene reactions coming up or subsequent chapters, we're going to see that we replace a lot of bad leaving groups with OTS, and that stands for this whole group right here. And so the OTS leaving group, it stabilizes the negative charge very well. So if you have the negative here, you end up with all kinds of resonance that goes all the way around these rings. So tosylates are going to be something that we see later, especially tosylates more than the other two. Here's some pictures just showing the resonance. Now, we've done resonance in the past, but you can see if we have a sulfate group here, we have an allylic lone pair, so we can do the 2-arrow resonance here. And then we have a allylic lone pair again, and this we can have the double bonds drawn in any position. So sulfonate groups are resonantly stabilized quite well. And if you add the benzene ring here, it's even more stabilized. You'll get this negative, this resonance going all the way around this ring as well. And you can see that their pKa's indicate how well stabilized the resulting anion is. Actually, correction here, that the trifluoromethane sulfonic acid, very acidic. Apparently this induction has a big effect on this particular molecule. This is the one that we usually refer to, and when we talk about the tosylates, though, is the resonantly stabilized sulfate attached to the benzene ring here, called the tosylate. And then we have just the methyl sulfate here. The tosylate, again, is going to be the ones that we look at the most. But this is a great leaving group, right? We can see that due to its pKa, that tells us that the conjugate base has a very stable negative ion here. So, as we said, like when we have an alcohol here or something, alcohols, if they're not protonated, are not great leaving groups. And so for what we might do is we might react an alcohol with a tosyl chloride here and pyridine, and we get an alkyl tosylate. Okay, that way here the tosyl chloride is to react and attach to the oxygen here, so we end up with basically a nucleophilic attack on the sulfur, and then the pyridine here is used as a weak base. A base, but that is not a nucleophile, basically. And so that is used to remove the proton, and then you get the alkyl tosylate. And this tosylate will be a great leaving group, a much better leaving group than an alcohol. So we're just kind of strapping the tosylate group to the oxygen of the alcohol. So it's really important to notice that there is no stereochemical inversion in this case, okay? No stereochemical inversion. So this reaction is going to be great for us when we have a terrible leaving group, like, or not so great leaving group like hydroxide or any alcohol. It's going to be very common to use tosyl chloride and pyridine to replace that with a better leaving group. And that way we can have a more ready substitution or elimination. So we can think about what we can do if we have a tosylate. And the tosylate's a great leaving group again. So this opens up possibilities to us. If we have a strong nucleophile and a strong base with a primary substrate, as we already know, this would generally give a E2 dominant, right? Well, with the primary substrate, it would generally give it, SN2 dominant with E2 as the secondary one. Remember, try to reason this through in your mind, right? Why does a primary substrate encourage the SN2? Oh, it's because it's less sterically hindered in the back, so the substitution can occur more easily. And so it's more competitive with the elimination. And so here the major product is going to be a substitution. Here the OH is substituting the tosylate, and the minor product here would be the elimination. However, if we have a secondary tosylate, again, that secondary substrate reduces the speed of the SN2 reaction. And so the elimination will become more competitive, and so the minor product will be due to the substitution. But having that tosylate on there, it makes for a great leaving group. And so both of these substitution and elimination reactions can occur a bit easier because of that. If we have alcohols, the alternative way to make a substitution or elimination with an alcohol is to protonate the alcohol, and then have have it leave as a better leaving group. So as we said, alcohols and hydroxide, terrible leaving groups here. And so what we can do is we can replace them with a tosylate, or we can directly react them with acid. And so what goes on when that happens is the first step in the substitution is going to be the protonation of the alcohol, which turns it into a decent leaving group. And then bromide, being a good nucleophile, strong nucleophile, will then attack the backside, and this will favor SN2 in this case because it's primary. And then the water will leave as a leaving group. And so here we can see water is a pretty good leaving group. It's nice and stable. Whereas, if we had not protonated it, hydroxide would be the leaving group. Not so stable, right? It's a pretty strong base. It's a pretty strong nucleophile, whereas water, weak base, weak nucleophile, not so reactive. Again, that's what we mean when we say stable, right? It's not as likely to go and react with things after. So the mechanism here here we have a tertiary alcohol. So notice the difference here. So this first slide was a primary alcohol. So substitution, SN2, very ready. It will happen. Not blocked off in the backside. However, if we have a tertiary alcohol, the substitution reaction, this SN2, will not nearly be as fast. Instead, SN1 will begin to become competitive along with E1. Remember, SN1 and E1 often compete. In this case here, we have again an alcohol. We're reacting with an acid to protonate it so that it will become a good leaving group. And in that case, now it can leave, and so here it is leaving. And that leaves us with this carbon with 3 bonds and no lone pairs. And so we have a tertiary carbocation intermediate, which is pretty stable. So that's why this SN1, this is SN1 mechanism, right? It's happening in 2 steps. The leaving group is leaving, and then the nucleophile is attacking. So this, if we want to encourage this reaction, as we said, if we want to encourage SN1 reactions or E1 reactions, we need to stabilize that carbocation intermediate. And those carbocation intermediates are best stabilized in protic solvents, meaning solvents that are like alcohols or water. They have an OH bond. If it's in a protic solvent, it's tertiary. It's got a good nucleophile here, a strong nucleophile, then SN1 will be favorable. But with primary, like we saw here, the SN1 would not occur because primary carbocations are too unstable to form. So primary alcohols would react via the SN2 mechanism, as we saw here. So primary alcohols react via SN2, tertiary alcohols here react via SN1. Here's if we use a hydrohalic acid, and this leads to more of the substitution product because the resulting after the alcohol is protonated, the resulting nucleophile is a great nucleophile, right? It will definitely go and attack that carbocation. However, if we use sulfuric acid, the sulfate is not a great nucleophile, and so sulfuric acid is used when we want to protonate the alcohol and have it leave and result in an elimination instead. And so if we have a tertiary alcohol and we use concentrated sulfuric acid, the E1 mechanism will be favored rather than the SN1. So basically, to summarize, if you have a tertiary alcohol and you want the SN1 mechanism to occur, use a hydrohalic acid as the reagent. If you have a tertiary alcohol and you want an E1 mechanism to occur, use the concentrated sulfuric acid and heat. It's a similar type of thing. We're drawing hydronium here because the sulfuric acid will protonate water to give us hydronium, because sulfuric acid is a stronger acid than hydronium. Then, like before, there will be a proton transfer here from the hydronium to the alcohol, which will protonate the alcohol. That will make it into a good leaving group that can leave. And then we have a tertiary carbocation here. We can now have the water, which is the primary solvent here, remove the proton. This will recover the acid, the hydronium, afterwards, and then we will get the elimination. This is said to be acid catalyzed, and we say catalyzed because the acid helps the reaction happen by protonating the alcohol. But it is not used up in the reaction because the final step of the reaction will then recover the hydronium. And so the E1 mechanism will be favored here. So finally, as we move forward in the chapter, we're going to have situations now where you're going to plan out what sequence of reactions you would have to use to make one reactant into a product that you want. And that is the foundation of organic chemistry, right? That's the main reason why people learn organic chemistry, and organic chemistry is used in industry, is to make new molecules that have never existed, right? And we can use these strategies and this knowledge of the OChem theory to choose the correct starting reagents and the correct the starting substrates rather, and the correct reagents and conditions to produce the product that we are interested in. And so as we move forward, we're going to see that starting with an alkyl halide, we can make a variety of substances by these SN1, SN2, E1, or E2 reactions. If we have an alkyl halide and we use a strong base, strong nucleophile like hydroxide, like this, here we have a primary. So notice the substrate here. So this is for if we have a primary alkyl halide, so if we have a strong nucleophile, strong base, the SN2 product will be favored. So we'll get a substitution. The OH will replace the bromine here. And of course, if we want to do a subsequent reaction on that alcohol, we will want to replace that alcohol with a tosylate, a good leaving group. If we want to remove the tosylate, this is a new part, we can treat with sodium hydroxide, and that will replace the tosylate again with the OH. Here, the tosylate's a great leaving group, so you can go back and replace it with the alcohol by substituting with the OH. If you want to replace the alcohol back with the acid, well, we use, if we want, this would be via a substitution reaction. We need to protonate the alcohol to make it into a good leaving group, and then the bromide ion can do an SN2 reaction and produce the alkyl halide back. Okay. So these are strong. This is strong nucleophile, strong base, SN2 reactions. This is also an SN2 reaction. This one would be an SN2 reaction as well. Now, if we have a tosylate that has a great leaving group, we can treat it here with a strong base. Here's terbutoxide, which happens to be a sterically hindered base, but in this case it doesn't matter because we only have one regiochemical outcome, is where the double bond forms right here. So this would involve an E2 mechanism. Strong nucleophile, strong base, strong nucleophile. For cyanide here, cyanide is also a great nucleophile, and so it can undergo a SN2 reaction here and make a nitrile, as they're called. If you have a nucleophile that's a carboxylic acid, you can have a substitution that will produce an ester. This is something we'll see later on, so this would also be an SN2. Here we can have a hydrosulfide, which will also undergo SN2 and make a thiol, or we can have an alkoxide ion, which will act as a nucleophile and replace the bromine, and we'll have an SN2 reaction, and we'll get the ether. Finally, if we use, these are strong bases, weak nucleophiles, so if we use those as reagents, we'll get an E2 reaction favored, and so we'll have the elimination here. Now for tertiary alkyl halides, of course the SN2 reaction will not proceed very quickly, right? The E2 can, but not the SN2. And so the result is that we have a lot less substitutions here. If we want to do a substitution, we may treat with water here, and that will the water will be the nucleophile, and we can get an alcohol. This will occur via an SN1 mechanism, right? So the first step of all these mechanisms is going to be the loss of the leaving group, which will produce in this case, the stable tertiary carbocation. So if you treat with water as a weak nucleophile, weak base, because this is tertiary, we can still get a reaction. We're going to get a mixture of the SN2 reaction and the SN1 reaction and the E1 reaction. We'll get about a 50-50 mixture of those. And so when the SN1 reaction occurs here, the water is added and then deprotonated, and we get the alcohol. And of course, alcohols are terrible leaving groups, so if we wanted to do a subsequent substitution reaction, we'd want to use tosyl chloride and pyridine and replace the alcohol with a tosylate, this great leaving group. If we want the alcohol to go back to the alkyl halide, this would also occur by an SN1 mechanism. As we saw before, the hydrohalic acid will protonate the water, which will leave, and then the bromide will attack. And so there's a kind of equilibrium that occurs here. When we have the tosylate, again, we have the choice of doing a substitution reaction or an elimination reaction. In this case, this shows the elimination products here. These are both E1s because it's tertiary. And the E1 mechanism here, this is an E1 too. If we have a sterically hindered base, we'll produce the Hoffman product, the less substituted product. If we have an alkene, if we have a less sterically hindered base, we'll produce the more substituted product. And these are E1s, so remember that we get every combination of stereoisomer here. It's not stereospecific, so it's stereoselective, but not stereospecific. So when we're thinking about synthesis, we want to think about what reactions, what reagents could we use to get the product that we're looking for. If we were building a house, we'd imagine what the house would look like. We'd make a plan, and then we'd get the materials, and we'd combine them in the right way. And organic synthesis is a lot like that. This approach is called the retrosynthetic analysis. This is where we, instead of looking at the reactant and figuring out what we can make, we look at the product and think, what could make that product? So you want to do both of these, moving forwards and backwards. Either way, might help you out to figuring out what you have to do. So let's say we want to make the following ether. We should think about what can make an ether. Well, an ether can be made if we have if this were an alkyl halide where this was the alpha carbon, and a alkoxide ion did an attack here at the alpha carbon and substituted what was already there. So we can do what we're doing here is a retrosynthetic analysis. We're saying that if something else were attached here, the alkoxide ion could attack and produce this. And so this arrow with the two lines with the arrow is meant to indicate a retrosynthetic way of thinking here. So we're saying that this can be made from an alkyl halide with this strong base, strong nucleophile doing a SN2 attack. This is a primary alkyl halide. So it can undergo a SN2 reaction. That would be the most favorable reaction for that primary alkyl halide with a strong base, strong nucleophile. And so that finally we can determine what the product is. There is an alternative. Often it's important to note that in synthesis there's often more than one way of doing things. And so alternatively, we could have an alkoxide ion here. We can make it from an alkoxide ion and an alkyl halide if this alkoxide ion here. So this would be, imagine this Na is a plus here, and we got all these here. So alternatively, we could have the longer chain on the alkoxide ion and the shorter chain with the bromide, but it would still work. We'd have an SN2. And so both here there were two possibilities, right? It depended on what reagents we could start with. So this is thinking backwards like this is a great way to figure out what you might need to make the product. And often thinking from the product backwards is the easier way of figuring out the synthesis. Finally, you think about it, you verify that what you've proposed is reasonable. So I was doing that along the way. I said, yeah, this is the alkoxide ion, the ethoxide ion here is going to be a strong base, strong nucleophile. We have a primary alkyl halide, so SN2 reaction will be favored. And we would want to do this in a non-polar solvent. You're going to see this is a polar aprotic solvent. And so this is going to be a very, very common solvent that we talk about as we move forward in reactions. Dimethyl sulfoxide, which is, I'll just draw it here. Dimethyl sulfoxide is this, DMSO. Polar aprotic solvent. So here, what would you need in order to make the following compound as a product of a substitution reaction, right? Let's think about it. Let's do a retrosynthetic analysis. If we had a nucleophile that is a carboxylic acid, okay, weak base, strong nucleophile here, and we have a primary alkyl halide, like this, this is bromine, we could have a nucleophilic attack, SN2 right here, and then the bromide could leave. So that's one way we could do it, right? And that would ultimately produce for us our ester here. Again, going back to solvents, remember that if we want an SN1 reaction to be favored, we should use a protic solvent because that will stabilize the carbocation intermediate. If we want a SN2 reaction, we want an aprotic solvent. Okay, protic solvents engage in hydrogen bondings and stabilize anions, so that stabilizing the anions is bad for the SN2 reaction, because it reduces the reactivity of your nucleophile, right? So aprotic solvents, these are going to stabilize both cations and anions, and that's good for an SN1, right? Because the SN1 has a carbocation intermediate, and so by using it, scratch that. Protic solvents, these will stabilize the anionic species. Again, this is bad for SN2. It's good for SN1 because it slows down the SN1 reaction, right? The aprotic solvents just generally stabilize everything better. And so if that's the case, then it's all even. And so then SN2 will be favored. Basically, we favor the SN1 reaction by slowing down the SN2 reaction. We slow down the SN2 reaction using protic solvents. Protic solvents, notice they all have a hydrogen attached to an oxygen or nitrogen. That's what it means to be protic. The aprotic solvents do not have that. And so here's the diagrams explaining why this is the case. If we have a polar aprotic solvent like this, we have this halide here. It's not a protic solvent. So all these ions are being stabilized. So if we stabilize the chloride ion, what we're starting with is a nucleophile here that is in a higher energy state. And by stabilizing that nucleophile, we get it closer in energy to the transition state, and thus the reaction happens more quickly. Aprotic solvents are good for SN2 reactions. That's the take-home message. If you want an SN1 reaction, you use the protic solvent. And so that's the end of this chapter. This is a big chapter. It takes a lot of practice, so be sure to do those homework problems and get a lot of practice. And I will see you all in class. Have a great week.